Okay, and I can take off the video mute. Okay, yes. Is that right? Is that okay? It's projecting here, but not there. Okay. I think this may not be the. Hold on one second. This I don't think is the right. Oh, sorry. Okay. Oh, I'm not sharing anymore. Okay, hold on. I'll do that. Okay, there we go. Zoom. Are we okay now? Great. Okay, so analysis of diffuse optical signals. And interesting. Okay, so this is going to try to wrap up everything you've seen in terms of diffuse optics during our short course. So we're going to, I'll reintroduce you very quickly to the standard diffusion approximation. We'll apply that to model reflectance signals in both spatial and temporal domains very quickly. I'll spend most of the time looking, kind of unpacking a little bit more detail the curves that Tom already showed you in terms of the sensitivity of both time and frequency domain signals to absorption and scattering. So you kind of get an understanding of what the curves look like and why they look the way they do and how they're sensitive to absorption and scattering properties. And how amplitude and phase, their characteristics in terms of how they impact the propagation of what's called photon density waves in tissue. And then we'll talk, we'll kind of return back to this kind of framework for looking at characteristic spatial and temporal scales and talk a little bit about, I wrote it in terms of pros and cons, but really kind of what are the situations in which spatial versus temporal domain techniques really have their best, they show their best face. Certain situations, you definitely want to go with a spatial domain technique, and in others, working in the temporal domain is definitely more advantageous. Okay, so this Rolf showed you this slide yesterday, and just to recapitulate very quickly, spatially resolved reflectance is a point spread function in space. We learned in lab yesterday that when you're probing source detector separations that are comparable to or smaller than the transport mean free path, typically increases in scattering will result in increases in reflectance. Because you're basically enhancing the direct backscatter. But if you're at source detector separations much larger than the transport mean free path, your reflectance will go down regardless of whether you increase scattering or absorption. That's intuitive in terms of absorption. Of course, more absorption you have, the more attenuation you'll get. But it's also true for scattering because the more density of scatters you have, the more path length you force the photons to undergo before escaping. All right. Yes.
So if I had the time domain source detector concentration,
yes.
Sources and detectors,
yes.
Is that spatially and time resolved together? So we're doing that together.
Yes, you are.
Okay.
Because what's happening is that, remember, a time resolved measure, if you integrate your time resolved measurement over all time, you recover a steady state CW measurement.
Yeah.
Right? Right? So basically, what you're measuring in CW, is basically, it's the integral over all time. So there's the relationship there. So in the spatial frequency domain, in a very crude way, spatial frequency is a reciprocal of some sense in position. It's a little more complicated than that because the Fourier transform, gives you contributions over the entire domain. But essentially, you can think crudely that small spatial frequencies are analogous to making measurements at large source detector separations. Okay? And high spatial frequencies are analogous to making measurements at short source detector separations. So in a similar way, just at large spatial frequencies, it's similar to making measurements at short source detector separation. So in the same way, you see increases in your spatially modulated reflectance when you increase scattering, when you're making measurements at large spatial frequencies. And how do you know whether your spatial frequency is large? Well, your spatial frequency is large is when the product of your length scale for transport times your spatial frequency is much larger than 1. Okay. Or another way you can think of it is that 2 pi k is much larger than 1 over L star. It tells you that the frequency is much larger than the length scale. Now, when your frequency is much smaller than the length scale for transport, you're going to be sensitive to both scattering and absorption. And in the same way as you have sensitivity to both scattering and absorption, you have the same thing here. If you reduce absorption, you're going to get increases in your spatially modulated reflectance at short source detector separations. And if you have more scattering, you're also going to also impact the reflectance. Okay, so you have sensitivity to both absorption and scattering at short modulation frequency. So the goal of this lecture is to give you these rules of thumb for these 2 remaining domains. Okay, and to understand some of the math behind it, or at least be exposed to it. I don't think I can claim to understand the math, especially in the temporal frequency domain. Okay. So you're familiar with this. I'm not going to go through this already. We already went through this in gory detail. But you're familiar with the radiative transport equation. You're familiar with the concept that to derive the diffusion approximation, you assume the functional form of the radiance is essentially an isotropic term plus a cosine theta term. You do the same thing for the phase function. And if you stuff these 2 expressions into the radiative transport equation, and you do some mathematical magic, you get this beautiful partial differential equation, okay? Which shares some commonality with the classical diffusion equation, which has this Laplacian term and a source and a first order derivative. But you get a couple things that are unique to light transport. One is this absorption loss term, which is not there in a classical diffusion equation, like a heat diffusion equation. And then you also get a wave-like propagation term, which appears in the P1 approximation, which those of you who are familiar with light transporters have probably heard that term. In the standard diffusion approximation, we get rid of this wave-like propagation. So that in the case where mu(s) prime is much larger than mu(a), this term is smaller. But the real important thing about this is that when we truncate the Legendre polynomial expansion for radiance and the phase function, we lose sensitivity to the phase function, and that we are able to adopt this similarity relation that all pairs of mu(s) and g that produce the same isotropic coefficient gives you the same solution. So you no longer care about mu(s) by itself or g by itself. It's just mu(s) times the quantity of 1 minus g that matters. Okay. Okay, so you played around with spatially resolved reflectance yesterday. This is the equation. This is really more for your own documentation. This is what the equation looks like for spatially resolved reflectance in steady state. One way to solve this is to do what's called a Green's function solution, which is the solution for a point source and do a spatial convolution. So this is the equation for the solution for a point source. The main attenuation coefficient is this mu effective parameter, which I should write here in case you're not familiar with that. That's a square root of 3 times mu A times mu S prime plus 1. It typically, I didn't put mu effective on this chart. It typically has a value of about, if I do mu effective, it's about 0.3 per millimeter if you do the math. And then to get the solution for spatially resolved reflectance, you have typically use a pencil beam, right, coming down. And so you get a spatially distributed source in Z, and then you can do the wonderful math. I'm not going to show it to you. It's in that paper that's referred to there. And then, you played around with this in the GUI, right? So these are Monte Carlo solutions to this equation. I don't think I'm going to belabor the points here, but typically standard diffusion equation does really well for high scattering. And then you see that even when you go to moderate scattering here, mu S prime mu S 10, yeah, it does fairly well, but you can even see deviations even at large source detector separations. Remember, this is on a log plot, so even small differences here are actually pretty significant. Certainly, once you get much higher absorption, it doesn't do well anywhere. Okay. We can also look at this in the time domain. So this is what we're here about today. Again, it's the same equations. We're going to get rid of this wave-like propagation term. The one thing that's very unphysical about the classic standard diffusion approximation is that when you have an equation that has only a first derivative in time, is that at time equals 0, just at time equals 0, you can have a system that has no light in it, and at time 1 attosecond, you will have some change everywhere through the medium. There's no finite rate of propagation in diffusion. And you'll see that when I show you the results of predictions of the diffusion approximation relative to the realistic Monte Carlo solution. So I'm not going to take you through the math, but you can generate solutions to this equation using the Green's function. So this is the Green's function now in the time domain. Okay. So you got variation with space and time. And it is again just a convolution of this Green's function with a temporally and spatially distributed source. The solution is this for the Green's function, but what's really interesting is that to generate some intuition, if you look at this, the solution of that equation in the limit of using source detector separations larger than L star. Okay, so say you have a source detector separation of 5 or 10 or 20 millimeters. That solution reduces to actually a fairly simple equation. So the time derivative of the natural log of the measured reflectance. So this is the measured reflectance that you measure at a particular location of time. Take the natural log of that and you look at the time derivative. It's actually a very simple expression. And you can look at this expression in 2 limits. You can look at it at the limit of long time. And what you see is that the slope, the temporal slope of that curve is essentially a constant. It's a constant that's linked to your absorption coefficient. And V is just the velocity of light in the tissue. Which basically means that if you're able to measure the slope of the reflectance with time, you can get mu sub A directly. And that's what Tom actually showed in his plots, where he kept scattering the same and he changed absorption. You see that the slope of that decay basically is linearly, on a log plot, is linearly proportional to the absorption. The other thing you see is that if you set this time derivative to 0, right? What happens when the time derivative is 0? You can have no light, but your point spread function, right? It increases and then it decreases. So when the time derivative is 0, where are you on that time? You're at the peak. Okay. So if you set this equation to 0, and you can actually isolate mu s prime, this is what happens. You can say, well, you can calculate mu s prime explicitly from knowing what your absorption is, but you know your absorption because you can look at this over long times. And you can find, if you can find the time at which you reach that maximum, and you know mu a, you can calculate mu s prime. Okay, so this shows you the separation of mu a from mu s prime, so long as you're far away from your source. And of course, you're in the diffusion approximation. Scattering is much larger than absorption. Okay. Okay, so that's really a really neat, simple way to think about the inverse problem. It's a little more complicated, but at least I wanted to drive that intuition. That knowing where your maximum is tells you mu s prime, and actually Tom showed that too, right? You kept mu a fixed, and you changed mu s prime, and you saw that mu s prime kind of moved a little bit to the right every time you increase the scatter. So the time to the maximum shift. Okay, so here's a little bit more gory detail here of the solid dots here are Monte Carlo. The solid lines are the predictions from the source, from the standard diffusion approximation. Yes, Ezekiel.
From yesterday, we were changing the distance between the
Yes.
When you do an actual experiment, you do first do a with the vectors, or
you could. I don't know, Tom. Are your source detector separations at all informed by the if you're going into an unknown or a new system? Are there any calculations you do to think about how you would configure your measurement? So there are two things that are involved. There's intrinsic sensitivity to your optical properties, but then depending on the tissue system you're in, you may be interested in probing certain volumes, and that's also impacted by where you put your sources in detectors. But it does certainly have impact on maybe the time resolution that you need to have, or what you're willing to tolerate in terms of your instrument response function. And that's something that we haven't really talked about here. That's actually really important, both in time domain and frequency domain, is the impact of, no system is ideal in terms of you never have this perfect direct delta function in terms of your source, or perfect sine wave in terms of your intensity modulated source. And then on your detection end, photomultiplier tubes are great, but it's not like they have instantaneous response with no temporal dispersion. And if you have temporal dispersion in your response, that's really going to compromise your ability to recover mu a and mu s prime, because you actually never detect these signals. These signals are so clean. In reality, your actual measure signal is dispersed in time, and they can also have humps in it, because PMTs are notorious for having this ringing after pulse. And so often you have a single rise, and then you have a secondary rise due to this after pulse, and that can really compromise in a massive way your ability to separate absorption and scattering. So we're kind of sweeping all of that under the rug in this context. Yes.
how do you calculate Tmax?
How do you calculate Tmax? I'm saying if you measure.
How do you measure Tmax?
Well, if you're getting full temporal response from your detector, then you could just figure out what is
practically used at the real.
Oh, okay. So there are a couple of different ways you can do this. I mean, in reality, you don't use those two simple equations. So two. Some people say, okay, I know my instrument response function. I can kind of deconvolve that out of my of what I measured to try to approximate what the signals would look like without the instrument response. In reality, what we do in our lab is that we try to do fits with Monte Carlo. We take the Monte Carlo output, and then we convolve that with the instrument response function. We compare the convolve, or you can convolve your SDA or whatever model with the instrument response function, and then you do an optimization between your measure and your model that has after you've put in your instrument response function. But it's the same sort of approach. Zico.
This graph that loaded is the actual measurements of the.
There are no measurements here. Solid curve is standard diffusion approximation. Dots are Monte Carlo simulation. So this is meant to show you where does the standard diffusion approximation work well and where does it work poorly. So the key thing here is that standard diffusion approximation is horrible at early times. And typically, what we do in our lab when we process experimental data with a diffusion-based model, because sometimes we do use diffusion-based models because they're fast. And if you want to have a real-time system, you want a model that's fast. And so we typically, you see that by the time you get to the rise, it's pretty good. So typically what we do, and remember, this is log scale. So you know, you're never going to have a system that has 74 to 72 dynamic range. But what we typically do is that we start fitting our data when our signal is about 80% below the max. That's when we start fitting the data. We ignore all the data below it because we know that the model is going to stay and it's going to bias the recovery. So we take the measurement and say, okay, let's find the time point where about 80%. Sometimes you can do half, sometimes you can do 80%. You know, depends on your system. Then we fit the rest of it. And typically, you know, time domain is good in systems where there's a lot of scattering, there's not a lot of absorption. You know, your signal drops massively, right? And absorption. And so, you know, this technology is good in low scattering and low absorbing media. Okay. Okay, this is where almost nobody uses time domain, but it's just good. So here I'm putting the detector at L star. Okay. You have massively attenuated signals at very short times. This is okay, you're not going to have a detector that's going to perform very well. But again, I just want to show you again, you're going to have, you know, way underestimate the time of arrival using standard diffusion. But even in these circumstances where standard diffusion, typically you say, oh, it's not good at source detector separations. Long times, it's still good because what you're doing is that you're only looking at the photons that travel these really long pathways. So it's true in CW, it's not good at this source detector separation under any circumstances. But in time result, it still works if you're way out there. But you also see that, yeah. So you can get away with it. Okay. And then I have more plots. I'm not going to belabor this, but you have this. And so now let's get to the fun stuff, the temporal frequency domain. Okay, so to kind of summarize in terms of temporally resolved, the key thing here is that time is linked directly to optical time. Okay? They're one and the same. You can even replace this axis by distance photons travel, you know, and just, you know. And at short times, increases in scattering result in increases in reflectance. At long times, increases in absorption or increases in scattering will reduce. Okay, so what happens in the temporal frequency domain? Okay, so I'll take you through this now. So typically what we do is that we Fourier transform. You can Fourier transform the time-dependent P1 approximation or the SDA. What we do is that we say, well, what you're doing in temporal frequency domain is that you're taking a source and you're modulating its intensity. So, and that's what this exponential I omega t represents. It represents an oscillation. And we say, well, if I'm putting in a source that is intensity modulated with time, well, more than likely their flux is also going to be modulating in time, but there'll be a phase delay and an attenuation. But if we, you know, basically put these two forms into the standard into the P1 approximation, the P1 approximation, you get this here. So you see that time is gone. What I should have done here is I should put R comma omega, right? So now I need to correct that. So all of the dependent variables now are R, location, and omega. Sorry, I dropped that. Okay. And I look at only the AC term, okay? Because there's also a DC term. And this equation looks exactly like your diffusion approximation in space, except that your attenuation coefficient here is no longer just a function of optical properties, also a function of. So this is your classic mu effective that, remember in steady state, your decay is mu effective, but here you're modified by your frequency dependence. Okay. And your frequency dependence, the importance of the frequency, the impact of frequency on your attenuation is dependent on the relative frequency relative to these time scales, where TABS is the absorption relaxation type that we just talked about, and T star is very similar to this T star. It's actually not exactly the same. Here we calculated T star as 1 over mu sub S prime V, right? Because I was just looking at what is the time scale for isotropic scattering. In this analysis, T star also takes into account absorption. Okay, but so it's like this. Okay, but in the context of where we typically use frequency domain, where absorption is low, that modification is really not. All I want to get through to you is that you have a frequency dependent attenuation coefficient, and you'll see an imaginary term. Okay, so what does that tell you guys? You have an attenuation coefficient that has a real portion and an imaginary portion. So what does that connote to you in terms of the frequency? When you have a real portion of attenuation. Yes.
Like an amplitude decrease.
That's right. So you get two things that happen to that wave as a result of its interaction with the tissue. You have amplitude attenuation and you get phase. So that's where this comes about. So you can think of it as, so what you can derive from this, I won't take you through that, is that you get an attenuation that's the real portion of the attenuation, which is the magnitude, and then you get phase attenuation. Both and the dependence of that on optical properties and modulation frequencies is complicated, but I'm going to try to hopefully give you a little bit of intuition of why that occurs. Okay. That's just my terminology. Accumulation shift. That's right. So that's accumulation. Right. The same. Yeah. Okay. So I don't know. I today for some reason I'd want to take you through the beauty of the math. The math is actually quite beautiful, but I think I really like to drive intuition because I think not all of you guys are diffuse optics experts or going to be diffuse optics experts. Some of you will, and you'll dive into the math on your own. So here what I've shown is the dependence of this. So K's are attenuation. So either the attenuation of the real portion or the phase. And the red refers to a highly absorbing material. The blue is a less absorbing material. The solid is the amplitude attenuation. So one thing you see very clearly, your attenuation goes up by about a factor of 3 between going from a highly scattered medium to even a moderately scattered medium. And that your attenuation of the amplitude actually increases slightly as you increase your modulation frequency. I've gone up to maybe an unrealistically high modulation frequency of 3 gigahertz. Tom would probably be rolling his eyes. It's like, we'll never go. But, typically, I think you go to what, 500, 600 before things crap out. But one thing I want to show you is that the real attenuation doesn't change much, so long as you're in at modulation frequencies shorter than this reciprocal absorption relaxation. Remember, we did this back abdominal calculation that the corresponding modulation frequency that corresponds to the time it takes a photon to get absorbed is about 300 megahertz. Okay, so I did a little careful calculation here. That's around 340. But you see that basically there's not much change in this amplitude of the attenuation with at these low modulation frequencies, and then you start to see a slight increase. One thing is really something that is not fully appreciated, I think, in the community is that this, I think in my view, I view this as an advantage, in the sense that the volume that you're probing when you're doing a multi-frequency measurement is changing. That's really a benefit. Often you're doing multi-distance measurements if you're doing, time resolved or spatial resolved. Even in spatial frequency domain imaging, when you're going from 0, say you typically take a measurement at 0 spatial frequency and 0.2, you have significant partial volume effects in all of those measurement domains. I think of all of the 4 measurement domains, frequency domain is one that, in some sense, across your parameter suite, if you're doing a single distance measurement, you observe the volume, which I think is really important to understand. It has great benefits. In terms of phase, typically in this modulation frequency domain, you have you start to see a slight turnover, but basically at these low frequencies, you get basically a linear dependence of your imaginary K vector with modulation frequency, which basically means that you expect a straight line when you're plotting phase versus modulation frequency. And then you start to see this turnover of that imaginary K vector, a larger modulation frequency, and that is due to scattering. So again, for small spatial, temporal frequencies, you get weak dependence of your the real K vector, whereas the imaginary attenuation is linearly proportional to F, and that just has to do with you're going to accumulate more phase if you have double the amount, double the modulation frequency. If you travel the same distance, you're going to accumulate double phase. For large modulation frequencies, you're going to have KR and KI, the imaginary real, start to approach each other and basically scale with the square root of the modulation frequency. Any comments, Tom? We're going to have more plots, of course, too. That's right. That's right. But you told me that actually low frequency is working pretty well. Yes. Okay. 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 So here I'm showing these plots in a slightly different way. So here I keep the location of the detector fixed at around 10 L star, keeping mu a constant. Okay. And I change the scattering. Okay. But when I change the scattering, it also means in order to keep the source detector at 10 L star, I'm also changing the detector. So here I'm just normalizing just to give you your attenuation. So you clearly see that that the higher your absorption, the more attenuation you're going to get with modulation frequency, but that you kind of get a turnover. I guess the second derivative kind of goes through maximum around this reciprocal absorption relaxation time. So you really start to accelerate your attenuation at these larger modulation frequencies. And then I'm plotting this phase in a very unusual way for the field, but I found it very intuitive. And let me try to convince you that why this is. So if you had a direct propagation from source to detector, no scattering, you would accumulate a certain amount of phase. That's no scattering. And what I did here is that I computed the phase, and I said, how much additional phase are so phi naught is the amount of phase you would accumulate if the photon went directly from source to detector, and you get no scattering. So it tells you that for so this is kind of like a differential path length. So it tells you that in a medium where mu(s) prime is 100 times larger than mu a, the path length that you get at your detector is basically 6 times larger than the direct path from source to detector. And what this plot is showing you is that so long as you're below this absorption relaxation time, you actually don't see much change in the differential path length of the waves that you're detecting. But then once you get past that, you start to get, especially you see this a little bit more in the 100 phase. You see a more accelerated decline in the phase. And so what that means is that as you go to higher modulation frequencies, you're basically cutting off light that has undergone these long pathways. Right? You're basically, because you're modulating so fast, faster than the light can be absorbed, you're not sensitive to absorption, and you're kind of getting only the earlier arriving photons, but you're cutting off the late arriving photons, which reduces your sensitivity to absorption, but does increase your sensitivity. Okay, and now I plot direct sensitivities. These are how does your amplitude change with absorption, and how does your phase change with absorption? So amplitude should go down as you increase absorption. That's why I have to put the negative here, because it's all positive numbers. You're going to have increased attenuation of your amplitude with increased. This is where I get confused. So we have, I guess it's really just it's a partial curve. Your absorption is low, but when you change absorption, your sensitivity to absorption is actually maximized in media where your absorption is intrinsic. And so this shows you that frequency domain is unique in that you have very good sensitivity in highly scattered media. But as your media becomes more absorbing, your sensitivity in terms of amplitude or phase to change the absorption. So that's why it's really uniquely situated to look at tissue systems. And then here you see that at small source detector separations, you don't have at small frequencies, temporal frequencies. Of course, you have no phase at zero spatial frequency, so you can have no sensitivity to absorption. But then you actually have very good sensitivity. There's a good temporal frequency dependence in your phase sensitivity to absorption, and that makes it, and it's non-linear, which makes your ability, or helps your ability to separate absorption from. But you see that you don't get that sensitivity, or at least a clear line shape in terms of spatial temporal frequency dependence of your phase due to absorption. You're actually less sensitive to that once you get beyond this reciprocal absorption relaxation time, because you're pulling off the photons that have undergone the large path lengths. So you lose kind of a signature for absorption through a sweep in temporal. Yes. Comparing which two? Which is superior? If you had to choose only one? Oh, I will defer to our expert. So if you're just interested in absorption, we just look at amplitude. Yeah. But even if you're looking at amplitude alone, you'll be sensitive to absorption, but will you be really able to discriminate absorption changes from scattering changes? No. So that's the thing. So there are two things here, right? There's the issue of sensitivity and there's issues of specificity. You'll be optimally sensitive to absorption changes, but you may interpret a scattering change and ascribe it to absorption. That's why you need both, because they kind of probe that orthogonal space. There's a lot of covariance issues if you limit yourself to amplitude alone or phase alone. Okay. And then here are the changes with respect to scattering. And again, here you start to see more nonlinearity at larger frequencies in terms of the sensitivity to scattering. But you really see the advantages in terms of sensitivity. So this is kind of this, these curves are really there for you as a resource, rather than me going to delve into a lot of the details. But I think this gives you a sense for, the value of amplitude and phase measurements, whether they're best situated for looking at changes in absorption versus changes in scattering. Ultimately, it's an ill-posed problem like all of the other ill-posed problems, and you'll have to, lean on your nonlinear optimization algorithms to try to do that separation. So the bottom line in terms of temporal frequency domain is that you're going to see reductions in amplitude with increases in either absorption or scattering, and that reductions in absorption, which kills off photons at shorter path lengths, and increases in scattering, which increase your differential path length, will both lead to increases in phase. And that's where your intrinsic sensitivity to amplitude and to absorption and scattering lies for amplitude and phase measurements. But the nice thing about this technique is, number one, your probing volume doesn't change that much with temporal frequency. And your volumes that you can probe are actually quite techniques, which is very, very advantageous. So I think I am going to end there because I know that Tom has some additional slides. So let's pause there while we allow Tom to get set up. Yes. Yeah. 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 Yes. Yes. That's right. I agree with that. And I think the added benefit is that your impact on partial volume effects is minimal in temporal frequency domain, but it's not in spatial frequency domain. It's quite drastic. And so, yes, just with that caveat in spatial frequency domain that you're not probing the same volume. Yeah. And maybe that's also why tomography is really hard for temporal frequency domain, because you have to really rely on geometry to probe the different volumes. You can't rely on just changes in optical properties to change your photon banana. So it's a it can be a blessing, but also a curse. Whereas I think, although there hasn't been as much work, I think, in spatial frequency domain in tomography, but I think there's a lot of opportunity to do tomography in spatial frequency domain that hasn't been realized yet. Yeah. Yeah. Okay, so let's pause there while we let Tom get set up. I'll open it up to questions, especially those that I cannot answer. Questions? Anna and Shashi are being too easy on me. Anna left the room. Yeah. Oh, thank you. Don't worry, people are just in shock. Too much Greek. Too much Greek.
Co-hosting it? I am. Okay, good. And just, and your microphone's not muted. Can you hear us? Okay.
All right. Whoa, look at that.
Multi-spectrum.
That's a new one. It's wow. Yeah. Cool. Let's try this.
God move to the left, we all move to the right now, or maybe should move to the right.
See what happens this time.
Here, glass of wine. All starting this up there.
There. Oh, okay.
Are they both back now?
Oh, let's try and it is, yeah. There we go. Nice.
Gabby, do you still see the talk?
Am I still sharing?
No, I don't think so. How about now? Okay.
There we go. Yeah.
Yeah.
So because I was grossly over time, Austin and I were discussing, I thought it made sense, and I think this was well too, is I want to talk about some applications, but I think it made sense for us to talk more about the computational aspects and modeling aspects. Because it was fresh in your mind, right? Before we kind of switch gears and talk about some clinical applications here. I don't need to hear anything. So those of you who work in this area, or those who don't, what do you think this would be good for? And I've got the obvious one up here, breast imaging, but what else? So brain imaging. Yep. Nation, hemorrhage. Yep. Peripheral artery. So how would you do that? Like,
You could do a little bit of probe that applies pressure. The way we do it in our lab is we apply pressure with the probe. and then
perturbation. Yeah. Refilling. Yeah. Absolutely. What else? Yeah.
I think picture how the baby's price.
Meat.
Yes.
Yeah.
The-
So not a clinical application, but a potential food application. Yeah.
the other picture, let's see how price.
Yeah, exactly. Yeah, I think that's actually kind of a very well suited area, these technologies. Yeah. What else? Plants? So, and I think the problem is having thick tissues in a plant would be tough for what we're doing, but I mean, I've got a colleague who does multiphoton microscopy on plants. He had pesticide concentrations and things like that. Yeah.
Say, maybe like muscular activation.
Yep. Exactly. Yeah, athletic performance, muscle gain, strength training.
even weight loss. We had a paper where we looked at the changing signs of the adipocytes in the abdomen during like a massive like weight loss. Yeah. With what? Okay, yeah. Cool. Yeah. Yeah.
Even we have a big,
Mhm.
external.
Yeah. Yeah. So I went through some literature and, tried to find where, particularly frequency domain and time domain spectroscopy has been used. And number of triggers, and we mentioned, peripheral vascular disease, neuroimaging, we talked about breast cancer, muscle and fat remodeling, joints. There's been looking at trying to image inflammation in joints with this technology. It's particularly challenging because we're no longer homogeneous medium. And the kind of stuff we talked about with CW, so intraoperative monitoring, neonatal intensive care, development, looking at sickle cell anemia. So a number of applications for these types of technologies. I'll talk about what we've been working on over the course of my career. First here at and it's looking at breast cancer imaging, and I showed you this picture before. As we talked about, there's many reasons this technology is particularly suited for breast cancer. Not the least of which is the optical properties of the breast are very well suited for these types of measurements. It's largely a homogeneous organ, which is nice for our models. The exception is when there's a tumor, and that perturbs that model quite well, so you need good contrast. And there's the elephant in the room of all optical imaging, which is we're not transparent, right? So there's always going to be a limitation of how deep we can get photons in and out again, and that limits on the order of 2 to 3 centimeters. So organs that are easily accessible, close to the surface where there's tumors near the surface, is a good application. And what was Qing Zhu, I think, published a paper once where she looked at the depth of all the tumors they measured with their frequency domain ultrasound system. And when we do these measurements, and the woman is laying back in a reclined position and the breast is flat, it turns out almost all of the tumors are within 3 centimeters of the skin surface. So that makes pretty much most of them accessible to this type of imaging. And in these tumors, we see what you'd expect in cancers: higher blood concentration, both oxy and deoxyhemoglobin. We see higher water concentrations because that tumor is displacing the adipose tissue, the normal fatty tissue that's supposed to be typically in the breast there. And I mentioned before, you can also kind of see that in the broadband spectrum. I always like to point out the relative fat peak and the water peak and see how that changes between different populations as the breast composition changes over time. So Bernard, we're going to do a demonstration later on DOSI. Is that in the cards? We'll see what happens. Yeah. So this may or may not be the system you see later, which does a combination of frequency domain and broadband continuous wave spectroscopy. This is one of those systems in my lab at Notre Dame with 2 of the short course alumni here, demonstrating how this is a probe-based technique where you take this and you scan this across the surface of the breast. This is the prior generation technology to the NearWave, which we're working on now, which we're trying to make it replace that with just something that fits in your pocket and you can do that scanning with. So, one area of promise for this is in non-invasive diagnosis or differential diagnosis of breast masses. we're largely driven by clinical problems. We should be driven by clinical problems. You know, we try not to be the engineers that are hammers looking for nails to hit, which is kind of how we started this discussion, but really focus on what are the needs? Where can we contribute to solutions? And, you know, perhaps diffuse optics is not the solution, but I think in this case, this is an area where it could be. And that is, at least in the United States, about 2 out of 3 breast biopsies come back negative. You know, which means for every 3 women who had got that core needle biopsy, which is a minimally invasive, but yet still painful, time consuming and anxiety inducing procedure, 2 of them will be negative. And that of course, causes a lot of unnecessary biopsies. It costs a lot of extra money spent. But I think particularly for these women who oftentimes need repeat biopsies if they have oftentimes there's a benign breast condition. It's when I work with radiologists and breast surgeons, we kind of use kind of slang terms, and one of them that comes up a lot is a busy breast. Right? Look at imaging, and there's just a lot of contrast, non-specific contrast that could be a tumor on mammogram. It could not be a tumor on mammogram or ultrasound. And, you always want to play it safe, right? Because you want to diagnose breast cancer early. When you diagnose breast cancer early, we can cure it. So that leads to this large false positive rate. So can we do something better, right? So going back to that picture of my foot, right? You've got mammogram, which is, X-ray imaging. Can that functional imaging provide additional information? So this was a retrospective study we did a few years ago, where we looked at all of the patients we had measured over time with this technology, many of them here at UC Irvine, but also at other sites where we had these technologies. And this is kind of a complicated plot, but the idea here is that you would measure, across the points of the breast over where there was some sort of abnormality. Oftentimes this was a cancer, but in a subset of patients, they were benign masses like fibroadenomas, cysts, etc. And the question is, by looking at that contrast, relative normal tissue or either on the same side or the contralateral side, can you distinguish what is benign and what is malignant? And, I don't want to spend too much time doing this, but the short answer is there was some promise to this. So by looking and training a model at the difference between malignant and normal tissue and doing a test set, right, you could distinguish with an area under the curve of about 0.9, which is already about as good as mammogram is. You could distinguish that and take that same exact model and apply it to benign versus malignant, and actually, somewhat surprisingly, it does pretty well in addition, right? So there are clearly signatures. In this case, it was deoxyhemoglobin. We looked at this over several different biomarkers. And deoxyhemoglobin makes sense because it's a marker, it's a surrogate marker of oxygen metabolism, right? So if you could think of, we don't have a direct blood flow measurement in this data, like doing DCS or something like that. But if you think of oxyhemoglobin as your supply, your arterial component, right? And deoxyhemoglobin essentially is what's left after that oxygen is metabolized. So we see an increased deoxyhemoglobin in those patients with malignancies. So when you start dividing it up, the numbers start decreasing, so we don't have a lot of statistical power to do that. But it's definitely something to look. I mean, it's certainly just dividing premenopausal and postmenopausal. Yeah. So in this case, I think it was just a logistic regression. Yeah, it was a pretty simple model. Yeah. What was kind of unique about this particular paper was using the statistical Z normalization technique. And the idea behind that was, this goes back to a point I made earlier, is we're very nonspecific. Everyone has blood, water, and fat. Every breast is different, right? Even among healthy, normal breast tissue, right? You can imagine there's different breast composition, sizes, et cetera. That's going to have different ratios of blood, water, and fat in it. So in this study, we looked at trying to normalize that in a statistical sense, and looking at the variation in these parameters in the normal breast as essentially a normalizing parameter was a smarter way to essentially have a control, a reference, rather than just what we were doing before, which is very simple, kind of lesion to normal. That motivates kind of the next work we were looking at is, but can we do this with an absolute measurement? You know, what if you didn't have a contralateral measurement or you had normal tissue to measure? Is there something more specific? So this led us to kind of examine the chromophores that we fit, and this is what we normally do, this is what we do now. And we have our deoxyhemoglobin, oxyhemoglobin, deoxyhemoglobin, fat, and water. And you know, this is a broadband spectroscopy technique, so we have all these wavelengths to fit to. And I was looking at this, and we always have areas that don't fit very well, typically at the extremes. And you know, for a while, and this contributed to it, you know, did this have something to do with the calibration of the instrument and the fibers? And it turned out that was part of it. We were kind of getting some inaccuracies in our calibration here, but even after we corrected for that, we kept seeing these, you know, spectral components that didn't fit. And we followed up on a paper that came out of here many years ago before I was here, where they specifically studied essentially the residual components. So, well, if you take everything away and look at what's left, was that predictive of cancer? And it turns out it was. It was actually quite powerfully predictive of cancer. So we decided to dive into this. Well, what is that? It's not some magical fairy dust that happens to be there. Long story short, what we found is it's methemoglobin. We found a good part of methemoglobin there, and I can talk in nauseam about this, but it's also important to include collagen in that fit well. And when you include both of that, not only do you recapitulate the total optical absorption well, as an absolute quantitative metric of malignancy, it was the best, right? Now, there's a lot of caveats here. Methemoglobin is a state of hemoglobin that normally shouldn't be in your body. So the idea is, well, if it's present, then there's something wrong. It's present where you find extravascular hemoglobin. So in leaky tumors, right, it made sense that you'd see methemoglobin there. There'd been some work, found one paper that looked at this in head and neck cancer. So this is the first time we saw it in breast cancer. But the caveat is it's still a really low concentration. Like we're talking sub-micromolar concentrations, which is right at the sensitivity limit of this technology. So if anyone asks you, what is your kind of chromophore sensitivity limit for this class of technologies? I would say, 0.1 micromolar is probably the best you could do, given the state of the art of the technology, signal noise ratios we could see, which is, not bad. 100 nanomolar concentrations, for a non-invasive measurement is not something to be ashamed of at all. So we looked at this in diagnostics. I'll leave you with the chemotherapy monitoring study. I don't know. Yeah.
Is it just you just catch it at the right time and see it?
That's a great question. Yeah. So as looking at this, we have a prospective data set, but we're not looking at this. But we do see a lot of variability. So that's quite possible. It's not something we consider. Kind of looking at that all the time.
Alternative is that it's not stable, but it's constantly being. Sure. It's constantly being moved down, and of course it's great, but it's also being replaced.
Yeah.
It is a nice, I think Tom saying it's a nice lesson on just because you can't get things that fit with what you have in the spectrum does not mean A, you're wrong, and the difference there to be quite valuable.
Yeah.
Yeah. I remember the first time Enrico's student described this. It made sense, and it was kind of profound.
Yeah.
Oh yeah. One person noises another person.
Absolutely. Yeah. Yeah. There you go. Yeah. So we are out of time. The other application we've seen a lot of success in is monitoring response to neoadjuvant chemotherapy. This was the topic of the large multi-center study that was led here out of Beckman Laser Institute, where we built those systems. We sent them to the 7 institutions to collect data. And the idea here is that so in neoadjuvant chemotherapy for breast cancer, the idea is you give chemotherapy before surgery, which is not the typical treatment. breast cancer. But it's done particularly in locally advanced cases where there's larger tumors, where there's a benefit to the patient to, one, not delay the chemotherapy. Right, we don't want to wait until we schedule surgery, let her heal up for 4 weeks and start chemotherapy, but the tumor is large enough where we want to get attacking any potential metastatic cells right away. So we want to get the chemotherapy right now. The other is to shrink the tumor, right, to make the surgery less significant. Perhaps you can do a lumpectomy and save the breast rather than having to do a mastectomy. That's why they do it. What Bruce realized was that there was a great opportunity to image these tumors during chemotherapy to get a sense of whether they're responding or not. And that was the purpose of this ACRIN study that when I was a postdoc here, I helped to launch this. And the idea is, can you tell, before the treatment is over, whether or not this patient is going to have evidence of that cancer at the end of chemotherapy? And still the clinical standard right now is if you're a woman, diagnosed with breast cancer, several friends go through chemotherapy, including my wife, you get the entire regimen no matter what, unless there is some sort of toxic essentially endpoint to stop that next treatment or delay it. So man, wouldn't it be great if, one, we could decide early on that they're not going to respond so that we could stop doing this, right? Because it's not helping. Or two, if it is helpful, right? And to help that person through the toxicities associated with that treatment. And this was really exciting because we looked at several different time points, but it turns out you only needed a few days, right? Only 1 week after that first infusion, we're looking at kind of 5 to 10 day time range here. If you looked at how that tumor oxygenation was changing, those that saw already a normalization in that tumor oxygen saturation were much more likely, right? 3-4 times more likely to be what we call pathologic complete responders, which means no evidence, pathological evidence of that cancer when they go on to surgery. So really exciting study. The results were exciting. What was not exciting was how difficult the technology was to use. So we started with 60 subjects across these 7 institutions, and we were left with 34 that we did. And the reasons were totally avoidable with good engineering and good technology, right? In some cases, the data was not collected properly. In some cases, the data was noisy. In the case of one institution, they decided to save time by not measuring the contralateral breast, which when the primary aim was lesion to normal ratio, right, you can no longer include that data in the primary analysis. So that, in summary, is what really motivated us to create something that was much more easier to use, faster to use, and really the goal of the company is to now do that type of study again to show that we can get good high quality data. Yeah.
Subjects.
Mhm.
17 of those are not responding.
Yeah, so it's typically about a third will be complete responders. So 2/3. Yeah, I mean, it's a bit of a simplification. I mean, you can divide that further. Some of those.
And it's still the standard.
Yeah. Exactly.
That's scary.
Yep.
For such studies, do they not do like an on-time test or to see if?
So they'll do that before they start to see if I mean, that's kind of the other reason is, before you start the therapy, can you select who's likely to be a responder? And there's already known, certain subtypes of cancer, like hormone receptor positive, are not likely to respond to chemo. So they'll do that ahead of time. What was really interesting about this study, I don't have all of the characteristics here. Of course, it's in the paper, it's a research paper, but one of the exciting things I found was for those patients who were hormone receptor positive, we actually could tell who was responding and not, which really is not a good way to do that, to know which of those patients would benefit from chemotherapy or not. I mean, certain subtypes like triple negative, we know they need chemotherapy, right? They've got an aggressive disease, we got to hit it right away. There's still work in developing therapies that are most effective for that, but there's a population where you're not quite sure if it's going to help or not. Yep. All right, well, thank you so much. Thanks for letting me finish. I saw you have a list of references. I got a list of references if you want to learn more. It's in the slides. I handed them on to be posted. And, just of course acknowledge the current people in my lab and those who are graduated and gainfully employed who've worked on these projects. And yeah, that's it. Lectures are over, right?